about our system called WebRelate, which is a new synthesis tool for integrating web data with spreadsheets. Now, consider this motivating example where you have a spreadsheet with a list of company names, and you want to get the stock value for each company. Now, this is the kind of a task that data scientists have to often do. So for this example, you could go to a web page that lists the stock price for Microsoft, and you can get the data from there. But clearly, doing this for all the rows in your spreadsheet is a very tedious task. So the other alternative would be to write scripts like this to automate this process. In this case, this script was written by an expert user, but clearly you cannot expect data scientists who are non-programmers to write scripts like this. So this is where WebRelate comes in. The idea here is that we only take in a few examples from the user and then automatically learn a program to do the desired task for the other rows in the spreadsheet. So I will show you a demo now so that you can see the workflow of WebRelate. Okay, so here's the interface to WebRelate. Let's say for the stock example, you want to get the stock information from this website. So first you would provide this URL to WebRelate, and then you can load the page. And then you would select the data that, from this web page. After that, you can just click a single button to do this task for the other rows. So in this case, WebRelate is actually learning two programs. First, it learns a program to get these URLs from the data in a spreadsheet. In this case, it needs to figure out that this URL is a concatenation of a constant string, and then the company name, and then another constant. So once it gets the URLs, it needs to learn another program to figure out how to extract the data. So this is a very simple example. Let me now show you some complex cases that WebRelate can handle. So in this example, you want to get the currency exchange rate between these two pairs of currencies on a particular date. And let's say you want to get it from this web page. So you can see that in this web page, the currency exchange rate is actually listed in a tabular format. So you can select the data that you want, and then click the Fill All button. So the challenging task here is that the system needs to extract this data, but this data is actually in a different location for each row in the spreadsheet, and that is actually dependent on the date that you have in the spreadsheet. And the other challenge is that the dates are in two different formats, so the system needs to learn some additional logic to do the transformation. So you can check that for the second example, it actually got the exchange rate for Jan 3rd with just a single example. So this is a case for where the extraction part is complicated. Let me show you a case where the URL learning part is complicated. In this example, you have a list of addresses, and you want to get the weather at each address. So in WebRelate, instead of directly providing the URL, you can also give a search query and then use a search engine. So we use Bing search because Microsoft. And then you can select the URL that you want to And then as usual, you would select the data and then click the Fill All button. So here, let me make it big. So the challenging part here is that this URL is more complicated than the ones we have seen before. First of all, the system needs to extract the city and the state code from those complex strings. So it needs to use some regular expression-based logic. And on top of that, this URL actually has strings like zip code that are not in the input. So our system actually uses a novel algorithm that can both leverage the given examples as well as the search results to learn complicated programs like this. So these are some of the cool demos. Let's go back to the slides to see how WebRelate works. Okay, so from the demo, it's clear that the high-level architecture of the system is first you have a URL synthesizer component that can take in the URL examples and then learn a program for generating the URLs. And then you have a web data synthesizer component that can then learn how to generate the data and this, how to get the data from the web page, and this data can also be conditioned on the input. So before I go into more details about WebRelate, let me briefly cover the related work. So previous systems for integrating web data with spreadsheets usually have a trade-off between user effort and expressivity. On one end, you have Data Explorer. It's fully automatic, but it is only restricted to transformations that can be learned from a single web table or from a single web form. On the other end, you have programming by demonstration systems like WebCombine and Vegemite. These can handle very complex integration tasks, but they impose more burden on the users because the users have to carefully provide demonstrations to reach the target web page for each example. So WebRelate takes an alternate approach. It learns the URLs directly as string transformations on the spreadsheet data. And by doing this, it can both solve complex integration tasks as well as with very little user effort. Additionally, none of these previous systems can actually do extraction from web that is conditioned on the input like we saw in the currency exchange example. So WebRelate is actually more expressive along that dimension. So there's another kind of related work for the algorithm side of WebRelate. So WebRelate is built on previous systems for learning string transformations like flashfill and blinkfill. If you don't know these systems, it's fine. You just have to know that the main idea of flashfill is if you have an example like this where you want to extract the initials from a name, then flashfill uses a technique called version space algebra to compactly represent the programs that do this transformation. In this representation, flashfill actually creates a DAG where you have a node for each index in the output. And you can see some possible programs here. For example, you can learn the entire string as a constant, or you could learn the R part as a substring from the input and the rest as a constant. Now, when you have many such programs, flashfill uses a simple ranking scheme that prefers substrings over constants to choose the desired program from this DAG. So with this background information, let's now look into how WebRelate works. There are three main core ideas. First, we frame both the URL learning part as well as the web data learning part as an instance of output constraint programming by examples problem. And this is more powerful than a simple programming by examples formulation. Second, we realize that version space algebra is slow when you have long outputs like URLs. So we devised a modification called layered version space algebra. The final idea is to combine the string transformation part with web extraction so that you can actually learn to extract data from web that is conditioned on the input. So I will go over each of these parts in more detail, starting with the output constraint PBE. So in a traditional PBE problem, you have inputs and outputs, and you want to learn a program that can transform the inputs to the outputs. In output constraint PBE problems, in addition to just inputs and outputs, you also have a list of possible outputs for each input. And for the URL case, you're getting this from using like a standard search engine. And in addition, you also have other inputs in your spreadsheet for which, even though you don't know the output, you still have a list of possible outputs. Now, all of this information is now available to the synthesis algorithm. And this is also true for the web extraction task. Here, the list of possible outputs are the nodes in the HTML document for each input. So this output constraint PBE, in short OPBE, formulation imposes two constraints on our programs. First, for all inputs, again, even for ones for which we don't know the output, the program should output something that is actually in the list of possible outputs for that input. And the second constraint is the uniqueness constraint. that says for the given input output examples by the user, the program should uniquely identify the output that is provided by the user. So these are two simple constraints. Now, why is this formulation better than a PBE formulation? First of all, it allows us to tackle a richer class of problems. So this is the example. This is the weather example that we saw in the demo. And this is a case that you cannot solve with PBE systems like FlashFill because you have strings like zip code that are not in the input. But in the OPBE formulation, you can use a search engine to get a list of possible URLs for this case. And now you can learn a program that looks like this, where some parts of the URL are actually a dot star, meaning they can match any string. So this will give you a regular expression like this, and if you try to match it with a list of URLs, it only matches one, and that is our desired URL. So the key idea here is that with OPBE, it is actually sufficient to learn a program that uniquely identifies the desired output from the list of possible outputs. The other benefit of OPBE is it enforces a natural ranking scheme for selecting the desirable program from the list of possible programs. So again, in the weather example, consider the zip code part and the weather forecast part. Now, both of these parts can be learned as either a constant or any string. So the question is, how do we know which part of the URL should be any string? We can answer this with the OPBE formulation. So you can immediately see that for the weather forecast part, it should not be an any string, because if you look at the list of URLs, making the weather forecast part any string would actually match both the first and the second URL, which violates our uniqueness constraint. And for the zip code part, if you learn it as a constant, it works for this example, but in OPBE, you also want to make sure that it satisfies the generalization constraint. So for the second input, this won't match any of the URLs. So that violates the generalization constraint. So that's our system is able to learn with just a single example that the weather forecast part should be a constant, but the zip code part should be any string. So those are the two benefits of the OPBE formulation. Let's now see how WebRelate can speed up the search process using layered version space algebra. So the main challenge with using version space algebra is that URLs are long, and the complexity of version space algebra is quadratic in the length of the output. Moreover, it's exponential in the number of examples. So for the weather example, even for a small portion of the URL, you would get a DAG that looks as dense as this, and doing anything on top of this DAG becomes very expensive. So WebRelate solves this issue by performing the search in layers. So we have increasingly expressive sublanguages, L1, L2, Lk. So WebRelate starts the search in the first sublanguage, and only if it cannot find a program in this sublanguage, it will restart the search in the second sublanguage, and so on. And the key part here is that the layers are designed in such a way that most common URL programs would fall in the earlier layers. Now, for this weather example, our layers would generate DAGs like this. You don't have to understand the DAGs much, but you can see that in layer 1, the DAG is very sparse. And yet, it contains very useful programs. It actually contains the program to learn this weather example. And you can see that layer 2 and layer 3 slowly adds more edges to the DAG. And layer 4 is, for the sake of completeness, uses the full DAG. But we don't have to go to layer 4 if you can find a program in the first 3 layers, which is actually very likely. So for the last part, let's see how WebRelate can do extraction that is conditioned on the input. So you can think of web extraction as learning constraints on how the desired node is related to the neighbors in the web page. And you can express such constraints in this query language called XPath. Similarly, this is the constraint for the currency exchange case. But in this case, the date is not a constant, but it's actually a string transformation program from the date in the input. So that's why we call these tasks as input-dependent web extraction. Although there are algorithms to learn simple XPaths from examples, we are the first ones that can learn complex constraints that look like this. So at a high level, our algorithm works as follows. We consider this input from the spreadsheet and this HTML tree where the target node is actually shown in red. So here the synthesis task is to actually find constraints in this tree that satisfy both the uniqueness and the generalization properties of the OPBE problem. Now, if you don't have the generalization property, you can just add all of those constraints. That would work for this example, but it would be over-specialized for this particular example. So because we have the generalization property, we actually do this in an iterative fashion. We consider constraints one by one and add them if they satisfy the generalization property, and stop adding constraints once you satisfy the uniqueness property. And on top of this, here we need to take into account that the strings are can actually be string transformation programs on the data from the spreadsheet. So to do that, we actually have to search for constraint in this tree where you would replace all the strings with DAGs. And these DAGs are actually capture the string transformation program that can generate the strings from the input. And by doing this, now we can learn constraints like this that are necessary for the currency exchange task. So here I skipped some details in the interest of time. You can find them in the paper or talk to me later. So those are the three main ideas of WebRelate. Let's look at some results. The first question we want to ask is the system expressive enough? And to answer that, our benchmark suite consists of 88 data integration scenarios taken from online help forums. And it covers a wide range of domains. And these tasks disintegrate into 62 URL learning tasks and 88 web extraction tasks. And for each task, we have about 5 to 32 input rows in the spreadsheet. And our system is able to solve all of them given enough examples. So I would say the system is expressive. The next question we want to ask is the system fast enough? Now here's a graph showing the time for the URL learning case. And you can see that all tasks take less than 1 second. So it is fast. Moreover, it is fast because of the layered search. If you don't use layered search, more than half of our benchmarks cannot be solved with a timeout of 2 minutes. Is the web extraction part fast? Again, here is the graph showing the running times. And we can solve all of the tasks in less than 10 seconds. The final question we want to ask is the system easy to use? That is, how many examples do the users have to provide before they can learn the desired task? So for the URL learning tasks, we can, WebRelate can solve 85% of the tasks with just a single example. You can also see the impact of the generalization constraint of the OPB formulation. That is, if you don't care about making sure that you have a program that generalizes to other input in your spreadsheet, you can only solve 30% of the tasks with just a single example. And for the other examples, you need more examples. For the other tasks, you need more examples. So this is also the case for web extraction tasks. You can learn 95% of the tasks with just a single example. And if you ignore the generalization constraint, the system needs to have more examples. So to summarize, I've told you about a system that can integrate spreadsheets with web data. And it does that by learning two programs. First, a program to generate URLs, and then a program to extract data. And there are three main core ideas: output constraint PBE, layered version space algebra, and input-dependent web extraction. Thank you.
Okay, so I think we'll start things off with an anonymous question from the internet.
Okay.
So someone's curious, how can the user check the correctness of the synthesized transformations if a large amount of data are involved?
So I guess currently they can just look at the data. So looking at the data is hard. So we actually even show the URLs. So at least for the URLs, you would probably be able to verify by just looking at the data. Now for the web extraction part, it's actually tricky because you have to click on each URL and then verify. But I guess you could have better visualization tools in future that will actually show you where you're getting the data from.
Any in-person questions? We have some more here too, so we'll keep with these. But if you would like to ask a question in meeting space, there are microphones or a microphone here.
Test.
Excellent. So another question was, can you use WebRelate in reverse to fill online forms across many pages automatically? Or I guess maybe adapt WebRelate to be used in reverse.
So you would fill the data with the spreadsheet. I guess you could do it. You probably need to invert the algorithms.
Is that hard?
It's not actually. The techniques can actually be adapted for any general integration task. So I think you could just do it.
So this is, I think, related to the first question you answered. But so what if the user doesn't give you the right type of examples and you can't synthesize? Is there some feedback that your system can give them?
So it is easy to give feedback because you, at least for the, so if you cannot learn a program, you can know that it's probably an error with the examples. So you can tell them, like, you can also tell them which example. We don't currently have it in the loop, but it should be easy to do those things.
Okay, so maybe one last question from the internet. How vulnerable is WebRelate to changes in web pages? Say, different placement of divs, change of colors, placement of advertisements, etc.
So our extraction algorithm is actually very robust because we satisfy both the uniqueness constraint and the generalization constraint of the OPBE formalization. So we can actually learn robust programs even if you have advertisements and other things.
All right, let's thank the speaker again.